Hi, we are Group 6 and we've been tasked to design a portal frame to create a practical warehouse using Revit and testing it in Spacegass analysis. This table provides you with an update of our progress and will clarify our material and structural design choices to meet our client's specification and also meet the Australian standards. The warehouse was required to have a roof pitch of 6 degrees and a roofing of Clip Lock Classic 700 with a building length of 24 meters, an eaves height of 9 meters, a rafter load of 10 kilonewtons per meter, a span of frame of 22 meters, and a wall cladding 24 millimeters of spandex. We were also required to construct a mezzanine level 4 meters off the ground and cover at least an 8 meter by 5 meter area accessible by stairs and should have a handrail surrounding it. In terms of layer site specifications and the load cases, this table here shows the walls and the roof spans that were used, and also the guards and the purlins used was C20015 and Z20015 respectively. All these were done using the Australian standards, which is shown here in this table here of concrete, steel, and loads. Incorporating Australian standards in Revit and Spacegass projects is crucial for ensuring safety, quality, and compliance with the local regulations.
Now let's discuss the Revit model. The ground floor plan will be 24 meters long by 25 meters wide. The slab itself will be 400 millimeters thick, while the mezzanine will be 4 meters off the ground and 8 by 5 meters in dimension. The north elevation shows the main door, while the south elevation shows the 5 windows located on the mezzanine floor. Here we can see the east and west views, along with more windows and a sliding door. Moving on to some sectional views, we have the longitudinal and transversal section. Here's a close-up of the transversal section. You can see the details of the slab, columns and beams. The 2270 by 2200 roller door was chosen as it's the largest one available. Due to the size of the portal frame build, it is assumed the space will be used for commercial purposes. Here we see some connection details. The fascia is used as a base to attach the gutters to, or as a cover to hide the fixing space between the roof, eaves and wall. The industry standard is to leave a 10mm gap between purlins and the universal beams to allow for error and expansion and contraction of steel. The bridging was not required given the sizing chosen for the purlins as well. And here is a 3D internal view of the mezzanine. This gives a pretty accurate representation of what it will look like when built.
We will now introduce you to our Spacegass model. Our Revit model was transferred to Spacegass and a full structural analysis completed on the Spacegass model to ensure that it is designed to meet AS 4100 standards. The location where the portal frame structure is intended to be built is the Wollongong area, which lies within the A2 wind region. Whilst the Spacegass structure followed the same specifications as the Revit model, we also had to consider that all concrete used within the model has a compressive strength of 50 MPa, all steel will be grade 350, any bolts and plates will be of commercial quality, and the assumption may be made that the pitch roof portal frame is pinned at the bases. From the 3D model, we were able to extract 5 primary load cases, which would later allow us to apply them to the 2D model. The first one was dead load, live load, internal crosswind, external crosswind, and internal longitudinal wind. The primary load cases can then be used in the 2D model to create the following 2 different types of combination load cases, which are serviceability limit state and strength limit state.
These combinations were created upon the client's request to show the portal frame strength under different scenarios. And as we can see, the strength limit states consists of dead loads, crosswind internal, crosswind external, and longitudinal loads. Now we will be looking at some different diagrams. Here we can see the displacement of the loads provided and the bending moment diagram of the loads. And next we can see the shear force diagrams and the axial force diagrams. And looking at these diagrams, we can get the idea of how much pressure or force the portal frame or the members in the portal frame can take without being altered in design. And from there we can sort of understand what materials or what changes we can bring in the portal frame to sort of improving the strength of the overall design. That would be all for our team. Hope you liked the video. Thank you.